All right, it's time for a lesson about vectors. So, physics involves vectors, and the topic is vastly deep. You can have an entire career studying vectors. And Isaac Newton was the genius that came up with, kind of the forerunner of understanding how to rationalize and calculate how things move. And it's very mathematical. And as a middle school science teacher, I find it a challenge to get students to work with and understand vectors because of the math behind it. It's like the math can be very intimidating. Yeah. Especially given the fact that so much of it involves right triangles. And while you may have heard of the Pythagorean theorem, you haven't heard of sine, cosine, and tangent, most likely, yet. So I've come up with a way, at least I'm strategizing to come up with a way that students can understand the math behind it visually rather than mathematically. Instead of numbers, we're going to use vectors, and like the length of the vector will be the number. So if I show you a vector that's this long versus one that's that long, obviously this one's twice as big, or approximately that. So that's what I want to do, and I think it'll be very rewarding. And what it will do for the student is allow them to see the concept without having to be bogged down by the details of the math. Yeah. So let's take a look at how that works. All right, so let's talk about how this stuff works. If I have a vector, and remember, this is trying to teach how physics works without involving a bunch of math. If I have a vector, maybe it's a tug-of-war team pulling this hard in this direction, and then another team pulling this hard in this direction, then the result of all that would be like if you just took this much off of this vector. So I'm going to make a mark right there, a new arrowhead right there. This cancels out that. So we take this away, take that away, and so the result is as if it were just one team pulling this hard. Now let me recap that. This team was pulling this hard at first, and the other team was pulling this hard. The result of these two teams pulling this hard and this hard is as if there was just one team pulling this hard. That's how you should think about. And physicists, they call this vector addition or subtraction because you're, adding and subtracting. And normally when we started out, remember the vector was this way, we might have 45.3 newtons. And over here we'd have some smaller number. Maybe you should have made that dotted. Some smaller number, so I don't know, 45, so 20 or 19.2. I'm just using decimals because in real life you never have nice round numbers. So you just take this number minus that, but that's using math, and students tend to freak out until they get good at math. But I would like to teach you students how to just visualize it, doing the math sort of instinctively, just artistically. Take away this from that. And that's how I want you to do this. So I don't think that's too hard. And this is just in one dimension, one direction. We can end up with problems. And let me emphasize the fact that if you get what just happened, you understand the basic, you really do get the basic idea. Where it could start to get more tricky, but still it's just the same thing as if we have two dimensions or two directions. So let's say you have a vector that's like this, then you have to be able to think of the x component of this would be as if the sun cast a shadow. If the sun was directly above, this would be the x component That's just the fancy term for the X, dimension. And then the Y component would be, if the sun was maybe about to set, it would cast its shadow on the wall. This would be the Y component. Okay? The reason you need to be able to do that is that when two vectors interact, like maybe there's another one like this, when these two interact, so imagine that this is some heavy object and there's a tug-of-war team pulling in this direction and another tug-of-war team slightly off. They're not in perfect alignment. Otherwise, if they were in perfect alignment, it would kind of be easy to cancel them out. You just take this amount and subtract that amount. But this is not in perfect alignment. It's actually off a little bit. So the X component of this guy would be something like that, and the Y component would be something like this. And so what you'd end up doing is you could just ignore, once you turn this black arrow into these two pieces, you could kind of ignore it. I don't want to totally get rid of it, but I want you to, pretend as if it's gone in a way, because it is being represented by these two. And then this one's being represented by those. So let me make it dotted. I'm only making it dotted because I want to kind of keep it there so you can remember where these things came from. But now what you do is subtract off in the X direction, subtract off that much. So right there would be the new arrowhead, and this would be gone. I'm going to try to make it dotted or faint. And then in the Y direction, you take this much away from that arrowhead, so you'd end up with a new arrowhead right there. And this would be gone. It's actually kind of a fun game if you ask me, the game of figuring this out. So the result of all this interaction is you end up with these two, and they create or produce a new vector like that. You can basically put them back together. Just like we took them apart, we can put them back together. That's the resultant of these two and remember, these black arrows are where we started. A tug-of-war team pulling like this and a tug-of-war team pulling like that. And the result is kind of as you would expect. This team would win by a certain amount, and now we know that it's this much. And it also, because this team was pulling slightly off to the side, you shouldn't be that surprised. And in real life, if you watch this happen, you'd know instinctively that this object is going to be kind of pulled off, off this line, because this team is pulling slightly that way. So I guess you could probably rationalize that because these guys are pulling a little bit this way, it's going to be off center or off this line by a little bit, but we also know it'll be in that direction because this team is pulling so much harder. And that's the technical way to break apart and reassemble vectors, vector addition and subtraction in 2 dimensions. But you have to know, for me to be able to ask you questions and communicate with you, you have to know some key terms. You have to know that this is the X component, this is the Y component, the resultant. I used the word resultant, or I said result. So that black arrow is the resultant. And yeah, it's really not that hard. And I hope this helps. I'll be, giving more tips as we go too, so.